that it usually makes. Okay, there it goes. Just took a minute. All right. So we're going to pick up today where we left off yesterday. So as a reminder, yesterday we talked through, well, let's go back 2 days. On Tuesday, we talked through variables, different types of variables, including numbers, integers, floating points, strings. We talked about various containers like lists and tuples. And then yesterday we talked about dictionaries. Then we talked a little bit about objects and how you can call methods on objects. And then we talked about control flow, and we talked about if statements and for loops. And then we talked a little bit about defining functions, which is kind of where we left off. So before I jump into continuing from there, I just wanted to ask if there were any questions from the last couple of days, anything at all. Okay. Again, just please feel free to interrupt me if you have any questions, especially people on Zoom. It's hard for me to monitor the chat or anything like that. Okay, so I have opened the notebook we were using yesterday. I'm just going to continue in that today. You don't need to do the same thing. It's up to you. But since I've restarted this notebook, as a reminder, none of the stuff we did yesterday will actually have been run this time. So here you notice if I just type true in a cell and evaluate it, I suspect, actually, I think maybe my connection got lost. Let me try refreshing this. I think my connection to the server got lost or reset there.
Is that what that asterisk means? Next to
the asterisk means it's thinking.
Okay.
So basically it's processing. So the reason I suspected that right off the bat was because when you evaluate something like true, it should return immediately. It shouldn't spend any time thinking. Let's try that again. Yeah. So you notice here that beside this cell is the number 1. And that's because this is the first thing this instance of Python has evaluated. And if we now evaluate false, that'll be 2 because that's the second thing. So that tells us that we've restarted our Python instance. It doesn't remember, back up here, entry 79 was us defining that Gaussian function we defined yesterday. So we know that that's been lost. And in fact, if we type Gaussian here, oh boy, I hope I didn't lose connection again. Is anyone else having trouble with the Jupyter Hub at the moment? It's a little slow. Probably means everyone's booting up right now in the other room. So it'll probably clear up in just a minute here. Let me go ahead and try restarting my kernel. Okay, seems to have come back. There we go. Okay, so notice that when I ask it to evaluate Gaussian here, which previously was a function that we had defined, and as we discussed, even functions are objects in Python, so this should have told us something about that function. Instead, it gave us an error, specifically a name error, saying, I don't know what Gaussian is. You haven't defined Gaussian. So basically that's saying, yeah, we've restarted the instance, so it's forgotten about what we did last time. So let's go ahead and redefine that function. As I recall, we had def Gaussian, and the first argument was x. That's just the x position that we want to evaluate the Gaussian at. The next argument was mu, and I'm going to do something a little different this time when we define it. I'm going to add what's called a default argument to mu. So usually when someone asks for a Gaussian, they want a standard normal Gaussian. They want something where the mean is 0 and the standard deviation is 1. And most of the time when people are going to call the Gaussian function, we can probably assume that that's what they want. So rather than force them to put 0 and 1 as the second and third arguments to our function, which is how we defined it up here. Let me make this a little bigger too. Hide this. That's how we defined it here. You would have to run it as Gaussian and then the x value and then the mu value and the standard deviation. Instead, we're going to provide a default argument. So we're going to say mu equals 0. And then we're going to say std, the standard deviation of the Gaussian, equals 1. Then we're going to just redefine the function. So we have to import math. And actually, I think the way we did it was we said from math import exp. I think that's how we did it last time, because we need that exponential function. And then we say y equals exp of negative 1/2 x minus mu divided by STD squared. Now, I think we might have had a slightly different way of writing that last time, but this is the same formula. And then we returned y. Oh boy, I hope this doesn't become a theme. It's still thinking here. Well, while the Jupyter Hub is having a little trouble, let me go ahead and explain a couple things about Jupyter. So if you're having this kind of problem, if you've got a cell that you've started running and it's not stopping, that can be a problem. And sometimes that can happen because you've made a mistake. So for example, maybe you made a loop that never ends. It's just going to keep going and keep going. If you do that, then you can usually interrupt the kernel by going to the kernel menu and saying interrupt kernel. Now, I don't know if that's going to work since the Jupyter Hub is having trouble right now, but usually if this would happen, that would be the thing I would do first, would be interrupt the kernel. Oh, that's a great question. So for the people on Zoom, the question was, what exactly is a kernel? So the way Jupyter works is Jupyter and Python are separate things. Jupyter is an interface. It's a server that runs this web server that we connect to. And when we open up a notebook and we start running Python commands, what Jupyter does is it starts up a separate Python instance that's running in the background on the server. And that's called the kernel. It's the Python kernel that the Jupyter is using to evaluate the actual Python code. So Jupyter is kind of a fancy interface that runs on top of a Python kernel and lets us have this nice interface for defining functions and evaluating things and printing stuff out. But you can also interact with Python. And since we're having a little trouble here with the Jupyter kernel, I think we may as well try this out. I'm just going to open up a terminal. Nope, I can't do that because Jupyter's having trouble. So I'm going to try reloading this again. Okay, so I'm going to come down here and launch terminal. Okay, so here I'm just running a terminal on the Jupyter Hub, and you can type Python, and it'll start up a Python instance. And anything we can type into Jupyter, we can type into this Python instance. It may be a little harder because this interface does not have very nice keyboard control and stuff, but nonetheless, we can do it here. So we can say x equals 1 and then ask for x, and it'll tell us that x is 1. So this is the actual Python interface that's running underneath the Jupyter server. So when you interrupt it, what you're doing is really sending it a Control-C, something like that. So if you push Control-C here, well, nope, it's frozen again. All right, so the Jupyter Hub is having enough trouble that I think what might be best is if I went ahead and ran a local Jupyter Hub. So let me see. So unfortunately, this means it'll be a little harder for you all to follow along. But this way, at least we can keep going. I can keep giving the lesson for now. If the Jupyter Hub seems to start responding better, please let me know so I can move back over and we can keep going from there. Okay, so where was I? I'm going to rewrite this Gaussian function that we tried to write. X mu equals 0, STD equals 1. I'm going to write this a little fast since we already did this. From math, we need to import exp. Y equals exp of minus 0.5 times x minus mu over STD squared, and then return y. Okay, so now if we evaluate Gaussian, we see that it's a function we've defined. Okay. Now, the purpose of giving these default arguments is that, like I said, you don't have to provide them when you request the value of a Gaussian. So we can now ask for Gaussian of 1, and it will run as if we passed mu equals 0 and STD equals 1. Similarly, we can ask for Gaussian of 1 when the mean of the Gaussian is 1. So when mu is 1, we can provide just mu. And when the when the mean is 1 and you ask for the value at 1, you get 1. And similarly, we can pass all 3 arguments, and that will work as well. Of course, asking for the Gaussian, the value of the Gaussian at 1 with a mean of 1 and a standard deviation of 2 is the same as if the standard deviation is 1, but nonetheless, we can pass these. Additionally, if you wanted to pass the standard deviation argument, but you wanted to leave the mean argument, the default value, you can call it like this. Say Gaussian of your x value, and then you can say STD equals 2. So this will override the value of the standard deviation parameter, but it won't override the value of the default value of the mean parameter. So this is like calling, this is like calling the Gaussian function with a parameter of mu equals 0 and STD equals 2. And there we get a different answer. Any questions about any of that? Okay. Is the Jupyter server still slow? All right. Sorry about that, everyone. Hopefully that clears up shortly. Okay, so before we move on and start talking about NumPy, which is what we're going to finish with today, I wanted to briefly talk about classes. So we've talked a little about types. We've talked about objects and how every object has a type. So for example, we can ask what the type of our Gaussian function is. Whoops, I misspelled that. I was going to say, surely my own computer's Jupyter server did not just crash. So the type of the Gaussian function is function. So that just tells us that the Gaussian that we defined as a function is a function, no surprise. But suppose we wanted to make a new type. Suppose that we wanted to define our own type. So just as a kind of simple example, let's suppose we wanted to define a type that tracks a 2D geometric circle. So to do that, we're going to declare a class. Class is sort of like an alias for type. You can think of types and classes as being pretty much the same thing. Class is just the keyword we use to define a type ourselves. So we can say class circle. Now in Python, it's traditional or it's conventional to define types to start with capital letters. And I don't think I mentioned this explicitly, but capital letters and lowercase letters in Python are different. So for example, the value x and the value x are not the same. So here we've assigned lowercase x to 1, uppercase x to 10, and we can see that lowercase x and uppercase x are not the same. So this is just to say that Python is case sensitive when it comes to variable names. So we're going to define a class called circle, and we write class circle and then a colon. And then much like with our if blocks and for blocks, we want to indent everything that belongs to this class. Okay, so typically when we define a class, we want to define some way that it initializes itself, and then we want to define some methods within the class. And the way we do this, to define the initialization, we define a function inside of this circle class. And Python uses a special name for its initialization functions, and that is underscore underscore init underscore underscore. So remember previously when we were running the dir function, we saw a bunch of underscore underscore built-in Python names. This is one of those. So it's 2 underscores init 2 underscores. And this function always takes the argument self as the first argument. Self will be whatever the new circle that we are creating is when we call this function. So when we create a new circle, what happens is Python goes and allocates some memory for that new circle, and then it calls this init function and passes that new object it's created as the self parameter. And typically when we create a circle, we're going to want to give it some center and some radius, right? So we need to know the x coordinate, the y coordinate, and the radius of the circle. So these are the things we need to know to initialize a new circle. And what we want to do is we want these to be variables attached to our new circle in some way. And we can do that by using a syntax like this: self.x0 equals x0. Self self.ynot equals ynot, and self.radius equals rad. So we haven't seen something like this yet, except we have seen the dot notation for calling methods, but the dot notation can also be used for variables that are attached to an object. So this is called a member variable, or a member value for this particular object, and we're just setting it to x naught here. Okay, so that's how we initialize our circle. So now let's define a method on it. And something we might want to do for a circle is be able to calculate its area. So we'll define a method called area. And all methods on objects, again, always take this self parameter as the first parameter. So the first thing that the method gets as its first parameter is the object itself. So we're going to say area of self. And the formula for the area is pi. Now, we don't have a definition of pi that we've imported. Pi isn't fundamentally defined by Python. However, you can import math, and math has a definition of pi in it. So we're going to go ahead and import math. And then we're going to say math.pi math.pi times self.radius squared. Now, because of the order of operations, Python will calculate this squared before it calculates the multiplication of pi times radius. So this will calculate the area. Yeah, Jessica, go ahead.
Yeah, quick question. So if you're defining like a calculation here, like I noticed you use self radius, like would it matter if you use rad because they're equivalent and it's run first?
Yeah, so that's a good question. So the rad, that's a parameter to this init function, it only exists inside of this block, this indented block. Outside of this indented block, that rad variable doesn't exist. It only exists for this scope. So we save it here as part of the object so that we can refer to it later. Does that make sense?
Yep, got it. Thank you.
Any other questions? All right. Oh yeah. Where does the init come from? Do you mean where does the name come from? I don't know the answer to that. I suspect that whoever wrote Python back in the 90s or 80s, I'm not even sure when Python was originally written, thought this was a nice way to have these double underscores was a nice way to signal that that was like an internal Python name. So the idea is you only use these double underscores when you're referring to Python internal things. You would never name your own function double underscore something double underscore. So I think it's really just a way of signaling that this is a special Python thing. That's all. But that's a great question. Okay, so last thing in this function is we want to return the area we calculated. Okay, so I'm going to go ahead and shift enter to evaluate all that. So there we've defined our circle class. Now, if we want to make an object of type circle, we can say C equals, and then we put the name of the type circle. And we don't have to pass these self parameters. These self parameters Python will pass for us. So we just need to pass these other parameters to this method, to this init method. So I'm going to say this is a circle at 0, 0, and it has a radius of 4. Okay, so again, this is an assignment, so there's no output from the cell. But if we now look at C, we'll see that it's some kind of circle. This is really all this is telling us is that the type is circle. This underscore underscore main underscore underscore is that basically when we import a package like JSON or like math, things exist in math in the math namespace. So for example, math.py exists in the math namespace. Things we define here on the prompt exist in this special underscore underscore main underscore underscore namespace. So that's why this is main.circle here. And this number here is actually just a memory address. So this is Python's way of saying I don't really know I don't know how to tell you about this circle very carefully. Can just tell you where it is in memory. So any questions about that? Okay. So If we ask for the type of this object C, we can see that it's a circle. And if we want to calculate the area, we call C.area. And again, we don't have to pass that self parameter we defined. Python will pass that for us, and we just call the area function by itself. And we get back a calculation of the area. Any questions on that? Okay, so there's a lot more to classes. Object orientation is sort of the theory of programming with classes and types like this. There's also a concept in Python called inheritance, where you can have classes that are basically modifications of other classes. So we could, for example, define some special kind of circle that always has a particular radius, and we could define it based on this circle class. But we don't really have time to cover that today. So if you're interested in writing more complicated programs in Python in the future, I'd recommend looking for some tutorials on Python object orientation and Python inheritance at some point. Or if you're interested, I'd be happy to talk about these at the review sessions or breakout sessions next week. Okay, any questions about any of this so far? Yeah. So when you're not inside of a cell, so I'm going to push escape there. You can push A to add a cell above and B to add a cell below. Yeah. Right. Yeah. So if you're in the cell, A and B just enter the characters. Yeah. Other questions? That's right. So that's a great question. So for those on Zoom, the observation was that in this Gaussian function we defined, we imported this exp function, but it was imported inside of this scope. It wasn't imported into the module generally. So if we just try to run exp out here, it doesn't know what it is. That's because the exp, kind of like these variables, only exists inside of this scope that we imported it. So the question then was, can we do that in the class? So could you put like here from math import exp? I think the answer is yes, but the way this works is a little weird, and it's honestly not something I do very often. So I think that will work. And what this will do is it actually defines a member of the circle class. So circle.exp is now that function. So that's a little bit of a, this is called a static variable. It's part of the class, not part of an object of the class. This is a kind of a more advanced object orientation concept, but essentially, yes, it does work, but it doesn't do exactly what you might expect. Yeah. Any other questions? Okay. So let me make sure there's nothing else I want to cover here before we go on to NumPy. I think this is fine. So there's also quite a bit more on classes in the lesson plans if you'd like to go learn a little bit more about them. So if you go to the notebook that's on the curriculum, you can find a little more information as well. Okay, however, at this point, we're going to switch tracks and talk a little bit about NumPy. So I'm going to try an experiment here. I'm not sure if this is going to work for everyone on Zoom, but we're going to try it. For everyone on Zoom, can you see my iPad screen?
Yeah, we can see it.
Great. Okay. Okay, so in neuroimaging, we're often dealing with, first of all, we've talked about lists and tuples and how they're a way to store collections of information, like a sequence of numbers, for example. And you can imagine that in a neuroimaging situation where, for example, let's suppose we've conducted an experiment where we've taken 100 different, for 100 different TRs or 100 different snapshots of the brain, we've taken these 3D images. So during the experiment, every second, we got back what is essentially a list of lists of lists of numbers, right? So a 3D fMRI volume, like the one shown here, this is basically 4 seconds of fMRI volumes. each of those is basically a 3D tensor of numbers, right? And if we needed to, we could represent these in Python as lists of lists of lists. However, there's some problems with that. So I just wanted to show you. I wanted to show you that image and make sure that that was going to work for later. Okay, so for example, we could have fMRI volume is equal to a list. These are rows. Let me make this look a little nicer. So we have a list. These are columns. These are slices. So we could have lists that contain lists that themselves contain lists, and this might just be one of our very first column, then we'll have another one, and then we have another one, and then this would just be the first row, and so we would have another row. This is a little bit clunky. This is obviously not a really convenient way to define these kinds of lists. And if we were going to, but let's suppose we went ahead and defined this fMRI volume in terms of this great big list of lists. So supposing we were going to do that, and we had some analysis that we wanted to run on our fMRI volume. So as an example, let's suppose that we've collected this bold time series. We have a 4-dimensional volume where we have X, Y, Z space and then time are 4 dimensions. And additionally, I've provided you with a brain mask. So I've got a single 3D volume where it's a bunch of ones and zeros, and every one in that volume corresponds to a voxel that's inside of the brain, and every zero corresponds to a voxel that's not inside the brain. And now you've got this bold fMRI image. And what you want to do is you want to just set everything outside of the brain to 0 in the bold fMRI image. So pretty straightforward task. So what I'm giving you here is the mask, which is a list of lists of ones and zeros. 1 in the brain, 0 outside. Okay. And then we have the bold volume, which is a list time of lists X, of lists Y, of lists Z, of bold responses. Okay. Does this kind of setup make sense to people? Let me go ahead and say this is lists X, lists Y. Whoops. Where? Oh, this in here? That's just telling us that this is input. Does yours not say in? It's probably, oh yeah, it's probably because there are little differences between this. I'm actually running Jupyter Notebook here, and I think you're running Jupyter Lab. So that's just a little difference in the interface. It's not a big deal. Okay, so but I just want to make sure that people understand the kind of setup here of the mask and the bold image. If there's any questions, please ask now. Okay, so again, our goal to set all bold values outside of the brain to 0. Okay, so we can do this. We know how to loop over things. So we can say for t in, and then we're going to have to come up with some notion of all the times. So what we need to know is how long that very outside list of the bold response is. And we can do that by asking for the length of a list. So if we have a list and we ask for its length, it just tells us the length. And additionally, there's one more function I would need to introduce here, and that's the range function. So the idea behind range is it gives you back a list of 0, 1, 2, 3, up to whatever number you ask for. So for example, if I say for k in range 5, print k, what this will do is it's going to print 0, 1, 2, 3, and 4. It's not going to print 5 because range gives you everything up to the value you asked, but not including the value you asked for. So that works like that. So down here, I can say for t in range of the length of bold. So this asks for the number of time components in the bold image, and we're going to loop over them. And then we can say for x in range len bold 0. So that will give us the length of the next nesting of list. And then we can say, or maybe actually better yet, we could say for length of bold t there. Then we can say for y in range length of bold t x. And then for z in range length of bold t x, whoops, y. And then we're down to the level of a single voxel, and we can say bold, well, we can say if mask of x, y, z equals 0, bold of t, x, y, z equals 0. This is real clunky and ugly. This would work, but it would, it's not a very nice way to write this. It's hard to read. It will be very slow as well. And the reason it'll be slow is because Python is not especially fast at loops, at least not loops like this. There are ways to write faster loops, and if you're interested in optimization of Python code, we can talk about that next week in breakout sessions and stuff. But these kinds of loops in general are quite slow for Python. And what we would really like is a more convenient way to interface with these kinds of data in general. These lists are great for a single list with just one depth of list, but they're not great as soon as you have matrices or tensors that are more than one dimension. So I'm not going to evaluate that because we haven't actually defined mask and bold and it would just fail. But I just wanted to demonstrate that this is a way we could do it. It's just not a very good way. So that's where NumPy comes in. NumPy is really, it's a general numerical math library for Python, but it has a lot of utility for tensors in particular, and matrices and vectors and things. So in order to use NumPy, we need to start by importing it because it's an external library. And to do that, we import NumPy as NP. Now, you don't have to import it as NP, but that is literally how everyone does it. And it's to the point where I think that doing it any other way will cause more confusion than anything else. So I strongly recommend always importing NumPy as NP. Some libraries are just like that. Everyone always imports them the same way, and NumPy is one of them. So go ahead and import that. Correct. Yeah. So the Zoom people, the question was, does that mean that when you call NumPy, you just always call it as np dot something? That's exactly how you do it. Yeah. So pretty much anything we do with NumPy will always be something like np dot whatever. Yeah. So for example, NumPy also defines the pi value. So if you import NumPy, you don't need to import math for pi. Now, NumPy operates on what are called Numpy arrays or n-dimensional arrays. And to make an array, we use the array function, np.array. So here I will just make an array 1, 2, 3, 4. And if we evaluate this, we get back an array 1, 2, 3, 4. Pretty simple. Now, arrays don't have to be just lists. They don't have to be equivalent to lists. They can be single numbers, for example. The number 0 by itself is a tensor, and so it's a valid NumPy array. It's just a 0-dimensional array. Similarly, we can make a matrix. So we can have, let's make this the identity matrix. So here I'm calling np.array on a list of 3 tuples, each of which is 3 numbers 1 0 0 0 1 0 and 0 0 1. These don't have to be tuples. I just do that because I think it's a little bit more readable. They could be lists instead. That's totally fine as well. But when we run this, it gives us back a matrix that's also of the type array. Okay. And I'm actually going to capture this. I'm going to call this matrix equals that array, so that we can look at it a little more closely. So there's a few member variables that arrays track that are very useful. The first one is the array's shape. So in this case, the shape of this array is 3 by 3, and that's because this is a 3 by 3 matrix. So this is just telling you kind of the dimensionality of whatever tensor you're looking at. Now, for something like for this vector, here I'm going to make a vector of floating point numbers. If we ask for its shape, notice that it returns a tuple, a tuple with a single value. And we saw, I think we saw this yesterday, where a tuple with a single value is put in parentheses with this little comma, and that's just to tell you that those parentheses are for a tuple and not for grouping. Because recall that if we evaluate 4 in parentheses by itself, that's just the number 4. But if we want that to be a tuple, we have to put a comma in there, and then it knows that that's a tuple. Any questions about that? Okay, now if we have just a number, like our 0 array, the shape of that is just going to be an empty tuple. That's a 0-dimensional array, so it's just a empty shape. There's another member of the array class that is very useful, and that's what's called the D type. So for our matrix, if I ask for the D type of our matrix, it gives us back this this D type int 64. Now I'll explain what that means in just a second, but let's also look at the vector of D type. So as a reminder, the vector is this 4-element vector of floats. And when we look at the D type of it, its D type is float 64. So what does this mean? Well, we know what integers are, and it makes sense that the matrix would have some kind of integer D type, because all we put in here is 1s and 0s, so these are integers. Similarly, these are all floating point numbers, so it makes sense that the type of this vector would have something to do with floating point numbers. But this 64 is actually indicating how much space this integer takes up in memory. And the reason that NumPy cares about that, whereas Python doesn't care about that, is because NumPy is really concerned with very efficiently representing numbers. So in Python, if you start with the number 0 and you start adding 1 to it, and you just keep doing that for hours and hours, eventually you're going to get to these enormous numbers. But Python's never going to tell you, you can't add 1 to this number anymore, it's too big. It will just keep making that integer take up more and more memory as needed. In Python, that's a really inefficient way to handle arrays, because you want your arrays to fit into a very concise piece of memory, usually. And so you want to know how much space each element of the array is going to take up before you allocate it. And that's why there's this 64 here. What that says is that these are integers that use 64 bits. That means that they can only get up to a certain size. I don't remember offhand what the size is for 64-bit integers. It's some quadrillions or something. It's really big. If on the other hand, this were a 32-bit integer, it would be able to go up to about 2 billion something. And we would be able to get as small as -2 billion something. Floating point numbers are a little more complicated because, as we discussed on the day one, they use this sort of mantissa plus exponent way of storing themselves. And that's not something we really have time to go into, but there isn't a really straightforward, simple biggest and smallest floating point number, because you have to deal with issues of how precise the number is as well. Regardless, 64-bit floating point numbers are pretty standard these days because most processors run on 64-bit code. And so 64-bit floating point numbers tend to be very efficient. They can get very small and very big, and I've never had need for bigger ones personally. Any questions about that? Okay, so what this is really telling us is that this matrix has a particular kind of integer as its entry type, and this vector has a particular kind of floating point number as its entry type. Okay, so let's look at a few other ways we can make arrays. We've seen this array function, which lets you pass in Python lists and tuples and things and turn them into arrays. But let's look at a few other things you can do. So first of all, let's make an array called X, and we're going to initialize it as an array just full of zeros. So to do that, we use the zeros function. If you're familiar with MATLAB, much like the MATLAB function zeros, there's also a function for ones, but that works exactly the same way, but we can basically say zeros, and then we can pass it a tuple, which is the shape we want it to have. So if we want to make, let's say, a 2x4 matrix, we can just pass 2, 4 inside of this tuple. And then when we look at what X becomes, we have a 2x4 matrix. Similarly, if we call something similar with ones, 2, 4, what we get back is a matrix of ones. Yeah, Jessica, you had a question.
Yeah, why does it make it as floats as opposed to integers?
Yeah, good question. So most of the time when people use NumPy, they need floats. That's just kind of the reality of how people use it. There's nothing, you can use it for integers. And in fact, if we wanted this to be integers, we could say np.zeros. We could pass 2, 4. And then we can pass an optional argument, kind of like we did. You remember we wrote the mu and std optional arguments. It's kind of like that, where we say the d type is equal to, and now there's a lot of ways to specify this, but typically you would just say int. You can also pass it a string int, that also works. But I'm just going to pass int here. And that'll give us back a bunch of integers. Another type you can actually use is, that's sometimes useful, is d type equals bool for booleans. And that gives us back a bunch of false values because remember, on day 1, we talked about how the value true is equal to 1 and the value false is equal to 0. So this is saying I want a bunch of zeros that are all Boolean, so I want a bunch of falses. Okay, any other questions? All right, there's also a function, much like in MATLAB, called I. I is for the identity matrix. If you want to make the identity matrix, for example, a 4x4 identity matrix, and I'm going to make one that is integers, just like that. So that makes us an identity matrix. Additionally, let's just talk about a few more of these functions. We saw the range function earlier. That was the Python built-in function that gave you back, for example, range of 5 is 0, 1, 2, 3, 4. NumPy has a similar function called arange, which stands for array range, I think. And it's pretty much the same idea, but it gives you back a NumPy array. Now, one of the nice things about arange is that, so arange works a lot like range, but range can only really work with integers, I believe. Arange works with pretty much any type. So we can, for example, say, I want a range from 0 to, but not including 5, and I want you to step a half step each time. So we didn't look at this way of calling range, but you can basically pass it the start, the stop, and the step. And this will go by steps of a half up to, but not including 5. A function that I actually find a little more useful most of the time is what's called the np.Lin Space Function. And it's a little bit like arange. The idea is you give it a start value, an end value, and the number of values you want between them. So I, for example, will say I want to go from 0 to 1. and I want there to be, let's just do 4 steps from 0 to 1. And what that's going to do is it's going to start at 0 and end at 1 and give us back 1/3 and 2/3 because they're evenly spaced in between. Any questions on that? Okay. In addition, there's another function that's a little bit like 1s, 0s, but instead of giving you back 1s and 0s, it gives you back whatever number you ask for. So this is a little bit like if, for example, we wanted an array of 10s, we could say 10 times np.1s, and this will actually work. This will give us a bunch of 10s. We'll come back to this in just a second, but there's also a function np.full, and we pass it a shape, and then we pass it whatever value we want it to put in the matrix. And this will also give us back a matrix of 10s. Now let's come back to this because there's something a little weird going on here. In Python, if we ask for 10 times a list, just a normal Python list, you might expect that this would return 10, 20. But in fact, what it's going to do is it's going to return a list 1, 2, 1, 2, 1, 2, 1, 2 with 10 repeats of 1 and 2. The reason for that is because Python lists operate differently when you try to multiply them. They're not intended to be numerical objects. They're intended to be collections of things. And so it thinks that when you add 2 lists together, what you want to do is concatenate them together. And when you multiply a list by something, you want to take that list and concatenate it to itself many times. On the other hand, Numpy arrays are intended to be tensors. They're intended to perform mathematical operations like plus and minus and times and stuff. So when we take a matrix like 1s and we add 1 to it, we get a matrix of 2s instead of getting a bunch of duplicates of that matrix. Does that make sense? Okay, similarly, supposing we wanted to do matrix multiplication, which is honestly one of the most important operations we do with numerical libraries, there is a function called np.dot for dot product. That's just a function. So as an example, I'll say I'm just going to use the identity matrix. Actually, let's have a matrix that doubles a 3-dimensional vector. So we're going to have the identity matrix for a 3-dimensional identity matrix times 2. And our vector is just going to be an array of -1.0, 0, 1.0. And we can ask for matrix, np dot matrix vec. And that will do the matrix multiplication of matrix times vector and gives us back the double vector. Okay. Any questions about that? Okay. All right. So in lists, we saw how we could not only take single elements of lists, but we could also take slices. For a slice, so I think since we defined vec, I'm just going to, well, vec's not long enough. I'm going to define a new vector. And actually, let's use an A range. We're going to make a range from 0 to 10. Just to see what that looks like, we'll go ahead and evaluate vec. Now, I can ask for a single element of vec. I can ask for element 5, which is going to give us back 5. But just like with lists, I can ask for a range. And that will give us back a sub array, basically. So this is saying I want the sub array of vector that starts at the 5th element and goes up to, but doesn't include the element 8. We can also index from the back of the list. And to do that, we use negative values. So if we want the last element in the list, we can ask for vec of -1. And if we want the second to the last element of the list, we can ask for vec of -2. Okay. Yeah. So basically, just to explain that, when you index a list, you usually count from the front. So element 0, element 1, element 2, etc. But if you want to index from the back, so you want the last element or the second to the last element or the third to the last element of the list, you can pass negative numbers in as the indices. So the -1 element of vec is the last element, and the -2 element of vec is the second to the last element. So anytime you have a negative value, it's kind of equivalent to vec of Lin vec -1, which will also give you 9, because the length of the vector is 10 and element 9 is 9. Does that make sense to everyone? Yeah. Correct. Yeah. So 0 is still 0 and it wraps back around as you go negative. Exactly. Okay. In addition, one of the really nice things about NumPy is it lets you get sublists that aren't just that don't just match this kind of range syntax. So for example, if I wanted to get the first, fifth, and eighth element out of this list, and just those 3 elements, I can pass it a list of the first, fifth, and eighth elements, and it will give me back those elements. That's something you can't do with lists in Python. If with a normal Python list, if I ask for element 0 and element 3, it's going to give me a bunch of errors because lists don't know how to interpret this. Only Numpy arrays know how to get a list of elements out of them. Okay. Any questions so far? All right, so we're coming up on the end of time for our session this morning. So I want to come back to that example we looked at earlier with the mask. So again, this time we have a mask, and it's some NumPy array, and it's full of 1s and 0s. I'm not going to define it here, so you just have to use your imagination. And then we have our bold image, which is also some kind of NumPy array. And if we were to ask for bold.shape, this would be something like let's say 100 time points and then 256 by 256 by 256 voxels. So again, this is the time dimension, and then this is x, y, and z. And our mask dot shape, after we've defined it, would be 256, 256, 256. So the mask is just x, y, z because it just contains 1s where the brain is and 0s where it's not. Okay, so in NumPy parlance, we don't need to write all those loops. We can actually use this very simple syntax, which is bold of tilde mask equals 0. That would be the whole, all those 4 nested loops we wrote earlier could be accomplished with this single statement. So let me walk through what that does. Now, I don't have these bold, mask, and bold variables defined because I'm running on my local computer here instead of the hub. But if we had to find them, well, let's just make some example dummy versions. So instead of having 100 by 256 by 256 by 256, I'm going to say that bold. And actually, this is a good place to introduce random drawings. So there's another function we can use to generate data, and that's called np.random.normal. This will just pull random draws from a normal distribution in whatever shape of array we want. So so actually, I'll go ahead and make it the right size. And in order to do this, the way we actually call this function is we give it the mean and the standard deviation, and then we say that the size that we want is this particular shape. So again, this numpy.random is sort of a sub package of the NumPy module that contains tools for randomly drawing from distributions. And this normal function will randomly draw from the normal distribution. I'm asking for a normal distribution with a mean of 0 and a standard deviation of 1. And we want it to draw entries for an array of this size of with shape 100, 256, 256, 256. I don't know why they decided to call this size instead of shape here. It's just something they did when they wrote the library. But regardless, that may take a second because that's actually a lot of numbers. And in fact, on second thought, I think I'm going to interrupt the kernel and draw a lot fewer numbers. So we'll maybe make this 2 by 25 by 25 by 25. Oh boy, I hope. Okay, I was going to get to that next. Yeah. So there we go. Okay, so I'm going to make a much smaller bold mass there. And I recommend you do as well, because that's a lot of 10 by 256 by 256 by 256 is a lot of RAM. Okay, and then we're gonna make a mask, and I wish I had a good way to make a simple mask, but let's just make a bunch of zeros for now. It's going to be 25 by 25 by 25 to match the shape of the XYZ here in the bold image. And then I'm just going to set a single voxel in the mask to be true. So this is, this is not a real brain, but we're imagining that we have a brain where there's just one voxel. So I'm going to say voxel 10, 15, 20 equals 1. Now, notice when we use lists, when we use lists, we couldn't use this syntax. We would have had to put a close bracket here and an open and a close and an open like that. And that will work. We can call this in this particular way to set that one voxel to equal 1. But NumPy, because this is a NumPy array, it also allows us to call it like this, which is just syntactically a little nicer. So I'm going to comment this out. Okay, now if we look at mask, it's a big array of zeros. This tilde operation flips all of those zeros from 0 to 1. Oh, I made a mistake. This mask needs to be an integer. Actually, it needs to be a Boolean, because those are zeros and ones. So if you use this tilde, that's an operation for not for arrays. So remember, we saw earlier that not true is false. Whoops. Not false is true. This tilde is basically equivalent to not for the entire array, for all of the array items. So when we say tilde mask, we get a bunch of trues back. And when we say mask by itself, we would get a bunch of falses back. Okay, so that's what that tilde is doing. But why does this work? Because it's not clear why this array of trues and falses would work here as an argument to bold. Well, one of the things that NumPy lets you do, and this is very similar to MATLAB, is you can pass it a list of true and false values, and what it will give you back is just the values that were true. So here, if I say true, false, it's going to give me back the first value and the second value, or the third value, because those are the values that are true. So we get back array 1, 3. Now, similarly, if I make an array and I say x of true, false equals 0, what it's going to do is it's going to set these true values to 0. So after that, we have an array 0, 2, 0, 4. So when we say bold of tilde mask equals 0, what we're saying here, this is a very concise way of saying, take that mask. Anywhere that the mask has a 0 in it, we're going to set that to 0 in the bold image. Now, I actually made another mistake here, which is that this wouldn't quite work because the bold image has 4 dimensions and the mask has 3 dimensions. So we need to tell NumPy that we want this to apply just to the last 3 dimensions of the bold, and we want it to apply to all the first dimensions. And to do that, we put a colon here and a comma. And the colon stands for everything in that dimension. So it's sort of like a star or something. So if we run that, that'll work, and then we'll have a bunch of zeros in our bold response. Now, if we wanted keeping in mind that when we defined our mask up here, we set this particular value to 1. So let's suppose now we want to go and check and make sure that our bold response still has non-zero values in that particular voxel across all the time points. So 10, 15, 20. We can come back down to the bottom of the notebook here. We can say, okay, bold, I want to get out all of the time points, and I want to get out just voxel 10, 15, 20 for every time point. And since the dimensionality of bold is 10, 25, 25, 25 for the time x, y, and z, this is going to give us back 10 values because of the 10 frames. And then it's going to give us back x, y, and z of 10, 15, and 20 for each of those frames. So that will give us back a bunch of random numbers because that's what we generated at the beginning. On the other hand, if we asked for bold of pretty much anything else, it'll just be, whoops, that was too big. Let's make 10, 15, 10. It'll just be zeros because we set everything else to 0. Okay, so I think we're actually out of time. We're actually a little over time. So I encourage you to go to the tutorial in the curriculum. There's a lot more information on NumPy there that we didn't get to yet, as well as some additional information on defining functions and some of the other stuff we covered. Please post questions in the Slack channel if you have other questions about Python. And if you would like to have like a review session or a breakout session next week on more other advanced concepts, I'm happy to facilitate that. But otherwise, thanks for coming to the 3 lectures on Intro to Python. And we have a coffee break outside now for everyone who's here, and we'll reconvene here at 10:30, I believe, for Dora Hermes's lecture. And we'll see you all then. Thanks, everyone.